All right, folks, welcome to another PyMCon session. PyMCon is a running conference where it's a running async and synchronous virtual conference where we get folks like Abuzar here to come tell us about all the wonderful work they're doing with PyMC. Of course, PyMC is the open source Bayesian PPL with a super fantastic code base and a lot of features, but we need folks like Abuzar to come use it to actually do all the statistics goodness, neural modeling, and anything else that you can do with Bayesian statistics to make it actually useful. For this webinar itself, we have a number of surfaces for you folks to ask questions. Let me just show them to you real quick. So let me bring up my screen. For questions, we ask that you post them on the discourse. The reason we do this is so everybody can see them for perpetuity. So I will drop the discourse chat, the discourse form in here. We'll be prioritizing questions that we see here. And then for PyMCon itself, you can see all of the talks that have taken place on the fantastic website that Porna has designed. So you'll be able to get to all of Abuzar's material, whether it's the async talk that he gave and posted before, the discourse thread, and all future and past PyMCon events. So with that, I'll give a quick introduction for Abuzar and the PyMCon session before we move on. Abuzar has already given a fantastic interview and an async talk showing everything that that he's going to be talking about, or at least the foundation of what he's going to be talking about in this session. He's going to give us another talk in this session, and then we'll do a Q&A at the end. So with that, don't want to take up any more of your time, Abuzar. Do you mind taking it away?
Yeah, thank you for that wonderful introduction, Raveen. Let me just share my screen. Can everybody see this?
Yep, it is visible.
Okay, lovely. All right, thank you so much for joining me today. I'm very excited to share my work using Changepoint models developed using PyMC today. The title of my talk is "The Only Constant is Change," and hopefully I'll share with you some of the interesting bespoke changepoint modeling I've done using PyMC. Right, to begin, I'll tell you a bit about myself, if my computer lets me. There we go. So I'm a computational neuroscience postdoctoral fellow in the CATS lab at Brandeis University in Boston, Massachusetts, and I study the dynamics of how the brain processes taste information. And we're always looking for more people, enthusiastic and interested in this kind of stuff. And so, the shameless plug: if you're interested, or if you know someone who's interested, feel free to scan this QR code or go to this website to see our position openings. All right. So to orient you to how this talk will go, here's a quick layout. I'll start with talking about some of the use cases for changepoint modeling, and I've broken this down into roughly 3 big categories. The first one is some examples of offline changepoint modeling, which I've seen are mostly used in research setting. Then there's the use of online changepoint models, which I've mostly seen used in industry settings. And then the work I'm doing with changepoint modeling in PyMC, what I study, how we use changepoint models, and a little bit about why we like using them and why these are the appropriate types of models to use to answer our research questions. I'll go on to briefly touch on the theory of finite and infinite mixtures to basically introduce us a bit to the mechanisms that we'll be using in some of the models I'll talk about today. And then I'll give an overview of the changepoint models I've already shared in the code. So if you're not familiar with it, I've already made an async video, as Raveen mentioned, where I go in depth into the changepoint models I've shared in my Jupyter notebook. These are all on the discourse page. So if you want more detail, please feel free to check those out. And with that, let's dive right in and talk about the different changepoint modeling use cases. And at any point throughout this talk, if something is unclear, please just stop me to ask a question. I might bump you to the Q&A section at the end, but if I'm missing something or if I skip over something, it's always good to stop there and clarify it. I'm not strictly monitoring the chat, so I'll ask the organizers to please point out any important questions. All right, so our first example is one of offline modeling, where in a lot of sleep studies in neuroscience, or let's say, even in a hospital setting, what people try to do is take EEG data, or in this case, the spectra of EEG data, and try to break it down into different chunks or different states of sleep using either change-point modeling, or if you're familiar with it, a hidden Markov model. And the goal is to basically describe this time series as a sequence of fixed states. And so to kind of more concretely point that out, if we look at this high deep state, we see this specific frequency pattern every time it appears. And similarly, for this low deep state, there is a different pattern that occurs every time. Every time you go from one sleep state to the next. And we can basically break down this continuous time series into these specific states to give a essentially more annotated description of it. Another case where you can use change-point modeling is to describe kind of like a moving average time series, where the authors of this paper use change-point modeling to kind of segment the time course of COVID cases into different epochs. And similarly, other people have used change-point modeling to be able to detect changes in forest cover. And so, these people monitored geospatial images, and they have different metrics like NDVI and SWIR2, which I'm not really sure how they're calculated, but the authors claim that they're used to describe the extent of forest cover in the specific image you're looking at. And these people were able to pin this date in 2019, where the forest cover in this patch of land in Myanmar suddenly disappeared. There was a sudden deforestation event. And so in these cases, in these offline cases, data was already collected and was analyzed post hoc. But in many industry settings, what people want to do is perform change-point modeling or temporal segmentation in an online manner. So data is collected and very quickly processed thereafter. And one of the more familiar cases of this should be how your smartwatches or smartphones are able to kind of segment your exercise history. And in this case, the authors were trying to use the accelerometer data from a watch to basically pull out sets of a repetitive exercise that the participant was doing. And here you can see that their model was able to pull out 3 different sets of exercising from this accelerometer data. Another online example could be trying to detect network attacks. In this case, the authors are monitoring data packets in a network, and using a change-point model, they were able to detect a sharp increase in the number of packets per sample. And the authors make it a point to note that this attack is not visible by the naked eye. So in cases like this, we'd like sophisticated change-point models to be able to precisely tell us something that a human observer would not be able to pull out from the data. And so the examples I've shown you so far can be broken down into roughly 4 categories. The first of them is trying to detect a change in mean, the other one trying to detect a change in variance. And of course, you can put both of them together and have a model which detects both a change in mean or variance. Or if you're familiar with kind of moving average kind of data, like financial markets or the COVID example I showed you, you can also try and detect a change in slope. For the work I'll be showing you today, it exclusively deals with models looking at changes in mean. And so before I go into the details of the analyses I did, I want to talk very briefly about how we collect the data that we use in studies in my line of work. So I deal with the neural processing of taste. And what this means is that we're trying to figure out what the brain is doing when you eat or drink something. And we do this using rats. And so we give rats solutions of different tastings. So sugar or sugar, which is sweet, salty, or quinine, which is bitter. And as the rat is drinking these tastings, we record from the rat's brain, and we're able to record voltage from neurons present in the brain. And we see that whenever neurons are active, they show this sharp deflection in the voltage around them. And this is what we call a spike or an action potential. And we're not really interested in modeling the exact voltage, but more interested in describing the activity patterns of the neuron itself. So how much the neuron is active, or when it's active, the patterns of its activity. So we basically extract the time points of these spikes into this binary time vector that we call a spike train. And neurons in the brain, all over the brain, respond to different stimuli, whether that's looking at something, hearing something, eating something, with specific patterns or temporal patterns of activity. And to show you a concrete example, here we're recording from one neuron. All of these data come from one neuron, where we've given sugar water to the rat multiple times. And so each repetition is what we call a trial. And we can see that every time we give the rat this solution, this particular neuron responds with a somewhat stereotyped pattern of activity, where in roughly the first quarter, this neuron is not very active. In the second quarter, it's completely silent. And then in about the last half of the data is when this neuron is very active. But here we're looking at just one neuron. But what we find when we record from multiple neurons at the same time is that all of them seem to show changes in their patterns of activity at the same time. And so they might not be increasing or decreasing in the same direction. So the direction of change for each neuron is not the same from one state to the next, but they do change at the same time. And I wanted to show you an example of some previous literature from our lab, which has used hidden Markov modeling to describe these kind of dynamics. Here, I'm showing you 4 rows, each of which is a different trial of a tasting given to this rat. We'll say that this tasting is bitter quinine, and it'll become clear why I picked quinine later on. And just to kind of zoom in on the data, if we look at this state 2 up here, we can see only 2 neurons are active. But when we transition to state 3, the top neuron kind of shuts down, and so does the lower neuron, but a whole bunch of other neurons turn on collectively. And this kind of data that can be accurately described in discrete states is exactly what a hidden Markov model or a Changepoint model is designed to do. And so in addition to the timing of transitions between these states, we can also get the activity levels of the neurons within each of these states, where the y-axis here gives us the probability of spiking within each state, and the x-axis is which neuron we're looking at. And so the reason we're interested in being able to describe these dynamics is because these are intricately linked to the generation of behavior by the animal. And so in this case, the transition into this blue state very accurately predicts the spitting response of the rat. So if we give the rat a bitter tasting, the transition into this blue state predicts when the animal will try to ingest that tasting from its mouth. And so the reason we want to use these Changepoint models is because they allow us to inspire and constrain theoretical models of processing in the brain. If you're familiar with something called an attractor network, it's a theoretical model of processing in the brain that elicits sharp state transitions. And by using hidden Markov models or Changepoint models and describing how these transitions happen in the brain, we try to constrain how these theoretical models can operate. In my work, I've specifically used these Changepoint models to study the strength of coordination between multiple brain regions over time. And that's what I'll go into over the next couple of slides. But I wanted to take a moment to basically ask the question, my lab had been using HMMs, which are trained using a maximum likelihood approach. And so why did I want to switch to a Bayesian framework, and why specifically to PyMC? And the reason I wanted to use a Bayesian framework was because, we like having uncertainty estimates. And in my case, for the previous paper I published, they were actually very useful because we were dealing with sparse data with a lot of uncertainty. And I'll show that later on. But specifically why I use PyMC was because I don't have a formal background in statistics or statistical modeling. So it was kind of impossible for me to write my own EM algorithm or a Gibbs sampler for the kind of change-point models that I'll be showing you today. And so PyMC allowed me to perform rapid iteration for model building. And as I'll share with you today, it allowed me to easily extend the models already built to specific use cases or specific limitations that I was seeing in simpler models. And along with all of this, it has really powerful inference mechanisms. Where in the latest iteration in version 5, the samplers are very well suited to even dealing with large data sets. And so with that, let's talk a bit about how I've used the change-point models I'll be talking about today. My work involved describing change points in the activity of multiple simultaneously recorded neurons in a brain region called the amygdala. So before my work, the lab I work in had only described these kind of changes in one brain region, the gustatory cortex. And so I was interested in, one, showing that this is not just specific to a particular brain region, these kind of state transitions, that they might be a general mechanism of processing in the brain. And the other thing was to try and use the coordination of transitions between these brain regions to say something about how strongly the regions are coordinated over time. And so just as an example, here are some 9 odd neurons recorded from the amygdala at the same time, and focusing on the transition from state 2 to state 3. The neurons underlined in green show a sudden simultaneous increase in their firing rate, and the neurons underlined in red show a concurrent sudden decrease in their firing rate. And if you were paying attention to the hidden Markov model examples I showed you earlier, similar to the gustatory cortex, what we find in the amygdala is that if you align the activity of these neurons to the time the taste was delivered, what I'm calling trial aligned here, these transitions seem to happen at different times along the trial. And so the transition time I've marked using red circles here. But when we align the activity to the onset of the state transition, we can see that indeed there is a very sharp change in the activity of these neurons. So to look at how strongly these regions are aligned in terms of their state transitions, I tried correlating the timing of the transition in each region. And here I'm showing 3 different trials of simultaneously recorded neurons from gustatory cortex and basolateral amygdala. And again, focusing on the second transition going from the blue state to the green state in this case, the yellow boxes indicate when these transitions are happening, and we can see that across trials they're pretty strongly aligned. And I was able to show that 2 out of the 3 transitions in the time period that we're looking at are much more strongly coordinated between the 2 regions than would be expected by chance. And chance here is shown by the black bars, which we generated using a shuffling procedure. But when we did this, we found that out of some 20 data sets that we have, only about 1/3 of them showed significant correlation in the timing of these transitions. And at this point, we wanted to know whether it's an issue with us estimating the timing of the transitions that's decreasing the magnitude of our correlations, or is it that we can find the transition time just fine and that it's just not coordinated. And this is where having an uncertainty estimate became very important, because we were able to show that there is a significant inverse relationship between the strength of correlation between these transitions and what I'm calling the normalized variance here. And the normalized variance is basically the variance of the posterior distribution of the transition time. And so the more certain we are about the transition time, the smaller our variance. And in those cases, the higher our correlation. And so this was very important for me and my supervisor to make sure that we're actually underestimating the strength of these correlations here, because neurons in the amygdala are very sparsely firing, so we don't have a lot of spike counts, and so it's hard for us to determine when in time those spike counts change. And it was also very important to convince the reviewers of how we were going about doing this. And so hopefully with these examples, I was able to convince you and motivate you that change point modeling is an important part of our analyses lives, and it has multiple use cases in both industry and research settings. And before I actually go and talk about the models that I've shared, I want to briefly talk about finite and infinite mixtures. And we will be one of the models that I've shared uses a finite mixture, and we won't be talking about a model that uses infinite mixtures, but we will be using some of the underlying mechanisms used in infinite mixture models. And so that's why I've decided to lump these together. So to start off with finite mixtures, if you have a multimodal distribution, there are generally two things, at least I want to try and do with these kind of distributions. One is to try and cluster data points to indicate which mode they came from. And the other is to obtain an analytical description of the distribution. And if your distribution looks as clean as this, the general attempt is to simply slap on some Gaussians on it. And where each Gaussian has its own mean and standard deviation. And then we can basically obtain an analytical description of this distribution by performing a weighted sum of these three Gaussians. And in this case, all of the Gaussians are roughly the same size. So I'm going to say that they all have roughly the same weight. The weights have to add up to 1 for it to be a valid distribution, but they don't always have to be even. In this case, one of the Gaussians is definitely bigger than the blue one's definitely bigger than the red one. And so it makes sense that it should have a much higher weight than the red one. But how do we actually, in a model, describe or generate these kind of distributions? What does the graphical model look like? And here is a graphical model for a fully Bayesian Gaussian mixture model. And by fully Bayesian, I mean that we also have priors on the parameters of the Gaussians themselves. And this figure I took from the paper mentioned here. And when I first looked at this, I was a little shell-shocked. I was like, there's a lot going on, not sure quite what's happening. But if we look at it a bit more deeply, we can break it down into essentially two parts. One of the parts are just the parameters for the Gaussians that we're generating, the mu's and so the means and the standard deviations for these k Gaussians. It could be 3, 4, 5, however many, the k Gaussians that we're generating. And then we have hyperpriors on the mean and the standard deviation for each of these Gaussians. But I think the more interesting part is how we actually calculate the mixture weights for each of these Gaussians. Because we're all familiar with Gaussian distributions, generating more of them is not that hard, but I want to dive a bit more into this mechanism for how we obtain the mixture weights for these distributions. Excuse me. And so the actual mixture weights come out of a Dirichlet distribution, which the parameters for which are dictated by this gamma distribution here. And a Dirichlet distribution simply returns us a vector of length k, where all of the elements will sum to 1. And so that makes it a valid distribution to provide us the weights for the different Gaussians that we're trying to sum up. To visualize this a bit more, here is a Dirichlet distribution with different alpha parameters, and roughly the magnitude of the alpha parameter dictates the value we'll get back from the Dirichlet distribution at the same index. So let's look at this 2, 4, 8 case. That would mean that the first element is half the size of the second element, which is roughly half the size of the third element. And obviously there's some variance in this, but again, trying to visualize it a bit more, let's look at a Dirichlet 255, where right off the bat, we should be able to say something like the first element is the smallest and the second two are roughly of the same size. But instead of looking at these distributions in this slightly obscure triangle, I like viewing draws from the distribution, which, as I mentioned, because all the elements need to sum up to 1, we can take each element as the fraction of a stick that goes from 0 to 1. And so the first element, is the smallest, and the second two are roughly of the same size in all of these 5 draws. But this raises the question of what happens when you don't know the number of components for a distribution, right? If we know the number of components k, we can generate an appropriate Dirichlet distribution for that number. But what happens when you don't know the number of components? Or if the number of components changes with how much data you have? And so both of these cases can be addressed by something called an infinite mixture model. And so I'm going to cheat a little and say that we basically have the workings for an infinite mixture model, because we can easily generate a infinite number of Gaussians. Because of numerical limitations, we generally don't work with infinite numbers. So we work with something called a truncated infinite mixture model, where k is just something very large, but it doesn't have to be a specific number. It doesn't have to be the number that you specifically want. It can generally be something larger. And so what I will say is that if we can find a way to generate a infinite dimensional Dirichlet distribution, then basically our finite mixture model will become an infinite mixture model. So we'll just try to take this k to infinity. And luckily for us, some smart people have already figured this out. So they claim that the infinite dimensional version of a Dirichlet distribution is something called a Dirichlet process, which again is governed by a vector of alphas, where each alpha is the concentration parameter for our Dirichlet process. And alpha dictates, essentially, if we take a stick again from 0 to 1, alpha will dictate how big each break off that stick would be. So going to this example here, the betas generated from our beta distribution with the vector parameter alpha will tell us how big the fraction of the stick that will break will be. And so our first break, B1, will be dictated by alpha, and then we'll draw another beta from this distribution, and we'll break off whatever is left of the stick. And then we'll do another break from what's left of that stick, and so on and so forth. And so this mechanism allows us to generate an infinite number of stick breaks. And this corresponds to what we were calling the infinite dimensional version of our Dirichlet process. And so this specific instantiation of the Dirichlet process that I'm mentioning here is called the stick breaking representation. And I like to use it because it's kind of simple to understand and simple to implement, but there's other flavors of the Dirichlet process out there, which I encourage you to look up. But before we move on, I want to focus a bit more on the role of alpha in how it determines the stick breaks that we're performing. So the smaller the alpha, the fewer components we'll have, and the larger they'll be. So if alpha is small, then we'll be doing larger stick breaks, and because of that, we'll have fewer breaks in total. But if alpha is large, then we'll have smaller stick breaks, but we'll have more of them. And to basically just look at how this alpha is changing the shape of the beta distribution, we see that in the case where alpha is 1, we have this beta 1, 1, which gives us an equal probability to draw both small fractions and large fractions. So our stick size, the breaks of our stick can be either very small or very large or anything in between. However, for beta 1, 5, which corresponds to this column here, the fractions or the length of the stick breaks are constrained to be smaller, and so we'll get more stick breaks. On the opposite end, we have beta 1 and 0.1, which would correspond to an alpha of 0.1 in this case. And in that case, we'll only get very large stick breaks. So hopefully with that, I was able to describe some of the important differences and similarities between finite and infinite mixture models and give you some theoretical background that will become useful later. But I wanted to take a moment to make some clarifications. The models that I've shared, one of them does use a finite mixture model, a finite mixture of emissions. The other is not an infinite mixture, but it does use the Dirichlet process in an important capacity. And I wanted to make this clarification at this point, was because I found the comparison between finite and infinite mixtures a convenient way to introduce these mechanisms, but I didn't want people to get confused by me talking about infinite mixture models and then never using them. So this is just a clarification. All right. So with that, I'll sweep through the Changepoint model code very quickly because I want to leave time for some Q&A. And so we'll start with what I'm calling the simple model, and then we'll go on to expand the simple model to address specific limitations that I'll introduce. The first one is trying to automatically determine the number of states that we should be using a Dirichlet process. And the other extension would be to allow drift across multiple trials using a mixture model. So starting with the first model, we basically have this time series of 7 neurons where the count of spikes for each of those neurons is indicated by the brightness of the color. And just by looking at it, we can say there's roughly 2 change points, one here, one here. But to describe this, to be able to have a generative model of this kind of time series in a state-wise manner, we need 2 ingredients. The first one is having the change point location, and so basically where our states start and end, and the other is having the emission values. So basically what will be the activity rate, the average rate of our neuron during each state. And so because we're using count data, we're employing the Poisson distribution, and the exponential distribution serves as a appropriate rate to feed our Poisson likelihood. On the other hand, for the change point location, we're using a beta distribution, which will tell us on a scale of 0 to 1 where the change point should lie, and then we basically scale it from the 0 to 1 scale to a 0 to 40 scale to mark in actual data indices where our change points should be. And when we run inference on this model, we see that the model, again, we told it we want 2 change points, and so it found the 2 change points that we were kind of looking for. If we look at the mean posterior predictive, we see that it does reasonably describe this data. You might say it's not fully describing all the variants, but it's doing a pretty good job of catching most of it. And then our inference for the change point location seems pretty strong. Our model is pretty certain about where these change points are happening. However, as I mentioned, we had to tell the model exactly where the change points, exactly the number of change points we wanted. And so wouldn't it be great if the model instead told us how many change points it thinks there are in the data? And to do that, here I'm using a version of the previous data set that's a little thinned out. So I've kind of reduced the number of counts, which adds a bit more uncertainty, because for me, that's the important part, whether our model can give us the uncertainty estimate in the number of states present in sparse data. And so now clearly there is still a change point somewhere around here, but you could argue that the rest of it is just one block. And so let's see what our model has to say about that. And so the emission component of this model is exactly the same. For each of our neuron, we're finding, or sorry, it's not exactly the same, but it's pretty similar. For each of our 7 neurons, we're trying to say what is the average firing rate in 10 states. And so going back to our discussion about the infinite mixture, now we're just using, a larger number of states that we need, but all of those states don't have to be used if our Dirichlet process, similar to the mixture, will tell us that, oh, the weight of this state is not that important, so we can just get rid of it. But instead of taking the weight of a Gaussian, we're using the breaks of the stick from the Dirichlet process to literally represent the duration of our states. So we're trying to find appropriate alpha and beta parameters for our Dirichlet process, which I've indicated by W raw here, which will return to us what the model thinks are the state durations that are present in this data. And so when we fit this model with, again, 10 states, we find that for our data, if we collapse all of the tau samples, the location of the change points, and plot a histogram, there are 2 bumps in this data. One is at the location of what we saw was the first change point in our previous model, and the other is at the location of the other change point. But this is just a histogram collapsed across all states. What can we say about state durations? So here, the fractional duration, again, is W raw. It's how big each state is. And for a model with 10 states, we can see that the model tells us that there's 3, maybe at most 4 states with a significant duration. And so even though the model tells us that there's about 4 states, it doesn't necessarily give us a discrete number. It's not telling us, hey, this has exactly 2, 3, or 4 states. It's telling us that these are the state durations. And so to get an idea about to extract the discrete number of states from this data, we can impose a threshold, where here I've said a threshold of 0.1 would be good, which means that if a state is less than 10% of the duration of the data, then we're not really counting it as a state. We want anything higher than 10% of the duration of the data. And when we do that, we see that we roughly have an equal number of samples, which suggests that there are either 2 states present in the data or 3. And having this distribution is very useful, because we know that it can't be anything else, or it probably isn't something else. But the model, it could be either of 2 or 3 states. And so this uncertainty will will inform the interpretations we make from these data sets. All right. Very quickly, I will run through the last model, and then we will move on to questions. So in the case of a bimodal distribution, I wanted to show this graph here to show that the mean of the distribution doesn't really describe either of the modes. And so far, the examples I've been showing you are of a single trial, right? A single pseudo trial, because I was adding the spike counts across multiple trials. But in lab, we actually deal with trying to find the location of individual change points on individual trials. And so while we find that the position of the change points is roughly static across all the trials, what does change are the emission values, or the activity of the neurons. And if those activities change significantly, then if we try to fit a model with the assumption, that the emissions are constant, then it will either try to fit to one mode, or it will try to fit to a mean, neither of which are good. And that not only poses problems for inference of the emissions, but also inference of the change points, because both of them are linked strongly. And so what we need to do is explicitly account for inhomogeneity or drift in the emission levels across multiple trials. And so these are the 7 neurons that we've been looking at so far, but now instead of summing their activity across trials, I've laid out all of the trials on the y-axis. And let's take one example. Let's take neuron 6. So the brightness of the color indicates how active this neuron is. And we can see that there are changes in time in this direction, but there are also changes across trials. For the first half of the trials, this neuron seems to be firing more in this middle part. But in the latter half, it's no longer firing as aggressively. And you can see that this is present, this strong change is present in all of the neurons as well. And so what we'll do is we'll employ a mixture of emissions instead of one set of emissions to model these changes in the emission rate of the neurons. And this model looks a little crazy, but that's because I've added a bunch of hyperpriors, because we're dealing with a larger data set, which is sparser now, because in previous models, we've been dealing with activity added across trials. And so for each single trial, we have smaller counts, but we have more data. So I'm using hyperpriors on both the change point location and the emission values to kind of constrain our model better. But it's the emission values and the change point locations are pretty similar to how we were employing them before. Now, for our two change points, we have to come up with, we have to find where they are on 30 trials. And similarly, for our lambda, for our 7 neurons in 3 states, we need to find 2 sets of emissions that we can use to describe this data. And those 2 sets of emissions will be weighted and summed for each trial using a Dirichlet distribution of size 30 and 2, where each vector of 2 for 30 trials will tell us how to weigh and add together these distributions to generate our data. And so when we perform inference, we see that the model also thinks how we were looking at the data, that for roughly up to trial 10, the weights of both mixtures was hovering somewhere about 0.5 for each. And then after that, there is a strong departure, and the model starts preferring one of the emission sets compared to the other, indicating a drift in the data. And so that's also very apparent here in the posterior predictive. All right, sorry for rushing through those, but at this point, I'll wrap up. Hopefully, I was able to show you why change point models are useful, how they are used in the world, and also hopefully how PyMC allows easy iterative development of bespoke Bayesian models, and in my case, change point models. And just some quick acknowledgements. I want to thank the organizer of PyMCon and their sponsors for allowing me this opportunity. Specifically, I want to thank Raveen and Purna, who were coordinating with me throughout this process. On the science side, I want to thank funding from the NIH to my boss, my fellowship from the Swartz Foundation, and Access CI, who give us computing allocations to run all of these models. I want to thank my boss, Donald Katz, for indulging me while I did this work, and Narendra Mukherjee, who first introduced me to PyMC. And with that, I'll take questions.
All right, I'll kick it off with a couple comments and questions. Also, of course, thank you, Abuzar, for putting this all together. You have such a wide-ranging presentation. So again,
my pleasure.
We haven't seen Abuzar's notebook or his async talk, you definitely should check them out. 2 other great sources of material. I have to say, I was super interested in this talk because change point modeling is what got me into Bayesian statistics as well. I had a specific change point problem at SpaceX. SpaceX makes different rockets, and I was specifically curious how the time to build a rocket would change between one iteration to the next. And change point modeling is what got me really, really fascinated with this whole field in general. But I did not take it to the level that you've taken it, Abuzar. Like the depths of the models you've taken, going from a simple model to a more complex one, to one that has a built-in HMM, it's quite awesome. I'm going to be stealing some of your.
My pleasure. Thank you.
4 questions. Let me ask the one I have on Discourse, and I see some other folks actively asking as well. The first one I had is, you show a slide, and I guess I'll just bring it up since it'll make it easier to ask the question. Just in the domain knowledge, is it that the state only changes in one direction? So you can't go from state 1 to state 2 to state 3 back to state 1?
Yeah, so that's a very good observation. In most cases, what we call the trajectory of the neural responses goes in one direction. And so given uncertainty, or given the noise of our observations, at least in this paper, the HMMs they use did allow transitions back to previous states. But in my work, to basically use simpler models, again, because I was dealing with sparser data, I took away, in my change point models only go in one direction. And so you have fewer states and fewer parameters to deal with. Okay,
that's easy. And that's a simplification that makes things easier.
We think it's largely true.
No, it's fair. And I had that question from your notebook as well. I saw you were using logistic regression to estimate states, and I was like, how does it go back? But I got it now. I thought I saw a comment on Discourse. Someone was typing, but let me maybe they're still typing it. Dustin says, I had one question, but you covered it beautifully, choosing a parsimonious K or kappa with a relatively sparse data. Thank you. An excellent presentation.
Oh, thank you, Dustin.
While I wait for other questions to come in, I'll ask you a couple more of my own, and I again encourage folks to take advantage of these 10 minutes while you have Abuzar here. Abuzar, the question I had was more about you and your journey on Bayesian statistics. One is you mentioned that a lot of folks you present to typically don't have a Bayesian stats background. You yourself were learning this with your team. Just in human time, when you see a presentation like this, it becomes easy to think like, oh, this person obviously knew how to go from an easy model to a hard model like in no time at all. Like, that journey collapses into just one stage.
presentation, right? Yeah.
But just for yourself, how long did it take, and what was your process for going from, like, I'm starting with a simple model like Cam David's pylons, TT dot, so like very, very easy model, then to your first model, then your second model, your third model. Just what was that time in that process like to build up to?
Yeah. So because this was initially this was something I was doing on the side, because I guess I'll start with a little bit of context. When I joined the lab, we were already heavily using hidden Markov models, but suddenly they stopped working. And because no one in the lab was a pure statistician, they couldn't explain exactly why that was happening. And so that's why I tried learning about hidden Markov models, but not having the theory background. I got kind of like mired in the equations. And so that drove me to PyMC, to kind of try and build my own Changepoint models. Once I started there, and again, this was a part-time thing related to my research, it probably took me a 2 to 3 months to convert Cam Davis and Pylon's what I'll call a single trial model, single time series model, into one that can also detect change points in across multiple trials. And then we also have multiple tastes that we give simultaneously. So basically adding 2 more dimensions to that change point model. And a lot of that was me figuring out in a very concrete sense, how priors work, what are the appropriate priors to use, what helps with sampling, and then doing the matrix multiplications to try and generate the firing rate in the back end that we will feed to our likelihood. So it was a lot of coming to grips with the mechanisms of PyMC. But I think, those 3 months, I was able to build a model, whereas I still, if you show me HMM equations, I'll be like, yes, that makes sense, but I wouldn't quite know how to implement it. And so that was time well spent. And then going from there, once I figured out these components, the Dirichlet process model probably took another month or 2 or so, and same for the mixture model. It was basically figuring out how the new component interacted with what was already there.
That's amazing, and I love how you combine multiple styles of modeling together, from Dirichlet processes and distributions to mixture models to HMMs.
Yeah, I think that's one of the great things about PyMC is that you have all of these parts just kind of already created, and I think the challenge was to figure out, one was the exact API, which has a lot of documentation, but the bigger part was how do I fit that in with what's already there. And so it makes things a lot easier.
Awesome. All right, let me get to a question that's been asked on the discourse, and even I think I might have an answer for this one, but let's see. Thomas says, what's the reasoning behind choosing a threshold for the number of states based on the duration of the data set? Why choose 10% as the threshold? Is it just data dependent? So I'll take a pass, and then of course you're the expert here. I think you answered this super well in your notebook in your talk why you picked 10%, and I actually really like the justification that you gave, but I'll throw it to you to answer this question here directly.
I actually don't remember exactly what I said in my talk, but the idea is, I don't have the picture in front of me, but if you go to that picture, you'll see that the job of the Dirichlet process is not to tell us 1, 2, or 3 states. It could, if you use, I think what's the Chinese restaurant process version of the Dirichlet process. But in this case, for the stick breaking process, it just gives you a continuous magnitude for each of the states. And so to convert that into states, you have to decide like what counts as a state, right? Like if a state is, oh, thank you. Could you scroll up to the previous figure? Yes. So here in the top subplot, you basically have to make a decision on what counts as a state, or what you're willing to interpret as a state. And if the duration of the state is 0, 0, 1 of the total length of the data, then is it really meaningful? Right? Like statistically, there is, it's very unlikely that any state will be 0, but you have to step in and kind of make that interpretation of this is a state. And so you could use 0.05 here. I use 0.1 because generally the states, because I'm used to seeing 3 to 4 states in the data I deal with. And so each state is roughly like 0.2, 0.25 of the duration of the data. But yeah, there is no threshold set in stone. It's more how I'm willing to interpret this data.
Thank you for that. For the extra context, let's see if there's any other questions. I see one more coming in, so let me give that person some time to write. We'll ask you another quick question, and then we'll get back from there. I was actually, where are you going next with this research? So are you at a state? Okay, I shouldn't use state because it's not. Are you at a point where your models are like good and you have what you need, and now it's just a matter of continuing on your research, or is there more that you feel that you need from these models to answer the questions that you're looking to ask in the future?
So I think I'm definitely, because I've been able to extend these models with reasonable ease. I'm trying to push the envelope. And one of the next steps that I'm really interested in is the assumption that we make with at least our neural data is that the states are flat, that once you're in a state, there's no change happening in there. But if you look more closely on single trials, you'll see that there are some internal dynamics present within the state. So I'm looking into things like autoregressive HMMs to try and see what are the internal dynamics present within a state. On the end of extending the models I have, I would be really interested in putting together a model that's kind of like a biased random walk for each state to try and model the dynamics present within, and that is related to maybe an AR1 process for a single state. But yeah, trying to get rid of the assumption that it's all flat within a state and try to see what is changing on a per state basis.
Got it. Okay. Great. This last post was just a comment, so I do not believe there's any additional questions. With that,
hopefully
then
that means I did a good job.
you did a great job. Again, between notebook and your pre-recorded talk and this one, you answered everyone's questions, Dustin, mine.
Lovely.
So,
and I just wanted to say that if someone has additional questions, my info should be on the discourse page. It has a link to my website, and my website has my contact info. So please feel free to reach out if you have any more questions or comments.
thank you again, Abuzar. And for folks actually watching this recording as well, you're always welcome to use PyMC, the PyMC discourse thread, both to ask PyMC questions and on this talk. People are still asking questions from PyMCon 2020 on tons of stuff, so that'll always be available to you. But I wanted to say again, thank you again, Abuzar, for giving this talk, putting together this material, advancing this data research, and taking the time out. As a personal anecdote, if you don't mind me sharing, Abuzar just got married, so we accepted this talk in September, but he's like, hey, can you guys hold off for a little bit? I've got a bigger thing to worry about for the next month, so I appreciate you. But he still put together material in between his wedding planning. So thank you so much for balancing this, your wedding life, your research, and everything else.
My pleasure. Thank you for having me.
For folks, the next round of PyMC talks are already scheduled. They're going to be in December with Ricardo and Alan Downey. So I think you'll enjoy that one as well. As always, go to the PyMCon website to see the latest and greatest, and also what's coming up, what also happened in the past. So you get a wide variety of Bayesian talks and Bayesian content. And thank you all for taking the time out to be here to watch this talk. With that, I will end the webinar. We'll see you all online in the community.